Welcome now on this module of advanced transport process, where I am going to discuss Newton's law of viscosity and shell momentum balance. That is the title that has been assigned for this particular module, but I will sort of handle this in a slightly different way, where in the handout we will mention something about shell balance, which is a very common approach, but I will try to convince you first so that you can convince it to your students that it is far better to talk about Newton's laws of viscosity from the basic concept of deformation of a fluid element. And I am going to present it like that. The handout will contain what I am going to present, and also you can have a competing statement for the shell balance approach. The logic that I prefer is that in the next module I will be talking about the conservation equations. So, the conservation equations are only dependent on the coordinate system, choice of the coordinate system, which you know, and therefore, it is also a reasonable approach to handle a fluid dynamics or a momentum transport problem from writing down the basic conservation equations and then depending on the situation cancel the terms which are not relevant to your system. I will follow an approach like that, which of course, it is a fact that now you are not teaching fluid dynamics to the students anymore, who have already done one course on fluid dynamics, and therefore, they should be well accustomed to the conservation equations. They have the concepts of steady state flow, they have the concept of fully developed flow and things like that, and therefore, I am going to present it in this particular way. So, I would like you to start, though it is a transport phenomena class, I would like you to start with the definition of a fluid, and then immediately probably it would be good if you talk about the two methods of description, that is the Eulerian approach and the Lagrangian approach, where you briefly mentioned that in Lagrangian approach you track the dynamics of each of the fluid particles. In contrast, in Eulerian approach it is sort of a fixed coordinate system, you track the overall motion of the flow or the flow at a particular location in the flow field. At this point I would prefer you to define what is a fluid particle. So, it is in fact not a bad idea to sort of talk about it as a sort of a packet of some fluid elements where the mass remains, fluid molecules where the mass remains conserved, but well the boundary can deform depending on the relative velocities that are functional in the neighborhood of that particle, that is whether you have some relative velocity or not. In fact, that is, you will all understand that that is exactly from where the concept of deformation comes in. So, once we have talked about the basic difference between the Lagrangian and Eulerian approaches, you can just run it in a revision mode. I would like you to highlight one of the most fundamental aspects of fluid dynamics, and that is the concept of substantial derivative. And I think the best way to do about is to talk about a steady non-uniform flow, where you simply have let us say flow through a reducer like this, and you ask the student that it is a steady state flow. So, upstream velocity is V1, the cross section at the upstream is A1, downstream velocity is V2, cross section at the downstream is A2, and you mentioned that most of the fluids that we are going to handle are incompressible fluids. So, rho remains constant, and therefore, what happens from simple mass balance is rho A1 V1 gives rise to rho A2 V2, and therefore, what immediately comes out is V2 is A1 by A2, sorry, this is A2 into V1. Now, from the geometry, since A1 is greater than A2, therefore, V2 is greater than V1, or you have an acceleration of the fluid element, though we have mentioned it is a steady state flow. And we all understand that this is due to the so called spatial component of acceleration, which actually is very, very important for fluid dynamics, or which is essentially the whole crux of convection based transport process. So, I think it is important that at this point of time you introduce the concept of substantial derivative or the so called operator ddt. right. And for that I think it's best to talk in a very simplistic fashion. You just assume, the detail will be given in the handout, you just assume that you have a generic 3D flow where at any instance of time t, the velocities and the coordinates are given like this, and after let us say time delta t, the fluid element has moved a little bit and its velocity is u plus delta u, v plus delta v and w plus delta w. Its locations, these are the velocity components, its locations are x plus delta x, y plus delta y and z plus delta z. So, now what we can write is that u plus delta u is actually the velocity, x component velocity at x plus delta x, y plus delta y, z plus delta z and t plus delta t. Now, also you need to highlight what exactly is delta x. Delta x is nothing but u into delta t and so on. So, if you simply perform a Taylor series expansion over here up to the first term, what you get is u as a function of x, y, z and t, and then you have del u del x into del x plus del v del y into delta y plus del w del z. I am sorry, this will be del u, these will be used, I just made a mistake. Del u del z into delta z plus del u del t into delta t. So, this is what it comes. Please kindly note the mistakes I made here. In the handout it will be perfectly all right. And then what we can write is that so what we can write, considering that delta x is equal to u delta t, delta y is equal to v delta t, delta z is equal to w delta t. If you simply substitute in the previous equation over here, so you substitute for delta x over here, delta y over here and delta z over here, and what you get is delta u, because you need to also understand that this u and this u, they are same. So, they actually cancel out, right, and therefore, what you get is delta u is u into delta t, because that is what stands for delta x, into del u del x plus v delta t into del u del y plus w into delta t del u del z plus del u delta t into delta t. So, all you are required to do now is to divide both sides by delta t, this term delta t, and take a limit for delta t tending to 0, right, and this is nothing but your substantial derivative or the material derivative, which gives you del u del t plus u del u del x plus v del u del y plus w del u del z. I just went on doing the entire derivation because from my personal experience I know this is a concept, students have very great difficulty, and once you explain this properly, you can now clearly highlight that fluid acceleration is different than rigid body acceleration, in the sense that in rigid body acceleration you always have a temporal term, and that is the only term. In contrast, in fluid body acceleration you have both a temporal and a spatial acceleration. So, this is very, very important to explain to the students, and once they understand it, you can actually rely on this to make significant further progress, including in the conservation equations. Conservation of momentum actually is nothing but a direct consequence of second law of Newton's second law, and in a way you can actually use this concept to straight away get to the advection terms on the left hand side. So, once everybody has understood the concept of the substantial derivative, I think we will you should move on a little bit to the concept of translation, rate of deformation, and finally to rotation also. What is more important to understand the Newton's law of viscosity is the rate of deformation. So, we essentially need to understand how a fluid element deforms under different conditions, and this condition is the condition of the flow field, whether there is, or more specifically whether there are relative velocities with respect to the fluid particle we are tracking about. Please do not forget, fluid deformation is a Lagrangian concept, and therefore we will focus on only one fluid element. I have come across questions, if you actually go deeper, where students ask, sir, you just draw that the fluid element is deforming, and 2 lectures later in control volume it does not deform. So, what is the difference? It is extremely important that you clearly highlight that the fluid element, the concept of fluid element is a Lagrangian concept, the concept of control volume is an Eulerian concept. So, these things if you clarify, the students have very good understanding, right. So, first thing what we need to look for this is that, suppose we talk about a fluid element of initial dimension delta x and delta y, and it is in a flow field where u is constant and v is constant. So, what will happen after time delta t? It will simply move from one location to the other location, but its dimension will remain exactly the same. So, this is translation without any deformation, and here the fluid element is behaving like a rigid object. So, this happens, you can have pure translation only under the situation where u and v are constant. Moving on, let us now consider that the same fluid element is in a flow field where u is a function of x and v is a function of y only. So, what will happen, what in very simple term it means is that if you look at the line ABCD, AB, the entire line is moving in the y direction at the same velocity, but the point B is moving at a different velocity in x direction as compared to point A. Therefore, this line is sort of going to stretch and expand. So, what happens is, after some time, let us say time delta t, you actually, the fluid element takes a configuration like this. Of course, you should highlight to your students that this textbook figure is actually wrong. Why? Because you cannot have simultaneous extension of both the lines AB and AD. So, actually if you, in order to preserve continuity, if one line expands, the other line should actually shrink in size if you are considering a 2D element. Of course, this is possible if you have a third dimension, and then this becomes possible at the cost of a reduction in the thickness of the fluid element. If you highlight these things, things become more understandable and clear to the students. So, what is the dimension of this particular segment? This particular segment turns out to be delta t, and the segment d1 is dv dy into delta y into delta t. This is because of the fact that the initial velocity at point A was considered to be u. but that at point B was u plus del u del x into dx. And if you now consider the velocity over here, that is the extra amount by which the line segment B has moved to its new location B1 with respect to the point A. Now, of course, what you can understand that the deformation does not have much meaning because it is a function of delta t, but what is important is if you would like to compare the strain rate, it is like, so you can define the strain rate in the x direction as the total strain per unit time, and the total strain is that delta L, simple concept, by L. So, which for the x direction will be B B1 divided by A B, and that turns out to be del u del x into delta t. Remember, we are talking about strain, and divided by the original length delta x. So, this gets cancelled out, and now if you are looking at the strain rate, what you get is whatever expression you have here divided by delta t. So, that gives you del u del x. Similarly, you can get an expression for the rate of linear deformation or the strain rate in the y direction, which will turn out to be del v del y. I will strongly suggest you that you encourage your students to write down the expression for each of the geometric segments and show it. Once this is done, it is important that we start talking about angular deformation also, and you know that. So, if you go stepwise, it becomes easier for the students to follow and understand. They do not try to sort of remember too much, which often is the case unfortunately with fluid mechanics. And now you simply have to say that you are talking about a flow field where u is a function of x and y and v is also a function of x and y. And as a consequence of that, the line segment AB is no longer moving with the same velocity, or all points in the line segment AB is no longer moving with the same velocity in the y direction. Therefore, if we assume that the y component velocity at B is higher than that of A, the line which was initially like this is going to sort of rotate a little bit or turn a little bit. That is exactly what is going to happen, and we all know that after time delta t, this is how actually they should have been dotted in the, please refer to the handout. This is how the element is going to look like, right? And so, this was our original ABCD, and let us say this is a temporary point B1 and this is a point B2, and this segment, the segment B1 B2, is actually dV dx into delta x into delta t. So, this section arises because of the fact that the y component velocity of all points in the y direction of the line AB are not same. Now, you also have a angular deformation here. So, the total, so this one can calculate as del u del y into delta t, right, and therefore, the total angular deformation is, sorry, I will write it as the total angular deformation is, so this if we mark as d alpha, and this if we mark as d beta is d alpha plus d beta, but again the problem is they are functions of delta t. So, they do not make much sense because they will go on changing with time. So, it is important to look at the rate of angular deformation, which is d alpha dt plus d beta dt, and which you now can find out that they are going to be simply dv dx plus del u del y. For this, kindly refer to the handout, it is all given out there, right. So, what we have found out, actually it is apparently we all only tend to write only these things, but it is important to tell that what we have done is we have found out that tan of d alpha, which is actually this b1 b2 divided by ab1, and then there are two approximations. One of the approximations is ab1 is approximately equal to ab, this is number one. The extension bb1 is much less, and then the second approximation is for very low values of alpha, d alpha, tan d alpha is equal to d alpha. Only under those limiting approximations you actually get this. So kindly take care to highlight all these minute aspects to the students, otherwise they have a tendency of mixing up things. So what we understand is that so what we were looking at is a particular xy plane, and what we have understood or what we have got is the rate of angular deformation is the summation of these two derivatives, or it is the, I would say a loose word like the cross derivatives, like del u how it changes as a function of del y and how del v changes as a function of del x, and that arises because you have a flow field where u is a function of y and v is a function of x, right. Now, based on this concept, I suggest that you introduce or relook the very, very well known concept of Couette flow to the students. And what you have is, this is, everybody knows this. So, you have a liquid layer sandwiched between two plates, and what you do is you apply a force which can be dfx or fx or dfx or whatever in the x direction, so that the top plate starts to move, and if you consider that the no slip boundary condition is valid at both the interfaces, then what happens is the fluid element or the fluid layer deforms like this to its new location A1 B C D1, right. And what we have here, we immediately notice that there is an angular deformation, right. And before that, let me just tell, so let's say A1 is equal to dl, and this dl is nothing but du into dt. So, du is the velocity in the x component and dt is the time over which this deformation has taken place, right. And you can also find out this d alpha over here. So, d alpha turns out to be, or tan of d alpha turns out to be a1 divided by AB. So, which is AA1 is now du into dt, you can write delta also, and then this AB is dy, right. So, again for the assumption that for small d alpha tan d alpha is equal to d alpha, what you get is d alpha is equal to du dt into dy, and consequently what you get d alpha dt or del alpha del t, probably I should have written del over all these places, is equal to del u del y. So, what we have got is rate of angular deformation is equal to the velocity gradient. Now, one can argue that this force has resulted in a shear stress, and what is the magnitude of this shear stress? You have applied a shear stress Fy, and the contact area over here is sorry, this is a force we have applied in x direction, and the contact area over here is, let us say, dAy, right, something like this. Kindly refer to the handout for all the details. Now, what we can argue is that this angular deformation has occurred only because of the fact that the shear stress was applied. This is very important. So, one can argue that this angular deformation is due to the shear stress that has been applied. Okay. And if we understand that, then of course one can write that this shear stress is some sort of a function, right, of this angular deformation. One can write it as proportional also, does not really matter, because it is also one type of a function. Sorry. So, you should be more specific in highlighting that shear stress is, let us say, proportional or is a function of this angular deformation. And now we know from here that this angular deformation is equal to the velocity gradient. Therefore, what we get is this is proportional to the velocity gradient, right. And this is a good point to really highlight the concept of a Newtonian fluid. Fluids where the rate of the velocity gradient and the shear stress vary linearly, or this proportionality constant, you just get it for a constant, that those are Newtonian fluid, right. So, this you can highlight, and this is also probably an important area where you should highlight that what are the non-Newtonian fluids where the dependence is not linear, and you can draw the usual figure for the dilatant and other type of fluids including Bingham. But that is not the whole intention what you should do, because viscosity you can understand. So, this viscosity actually is this proportionality constant and nothing else, but then again there are physical significances of viscosity which you can highlight. But what is more important is to highlight to the students that what we write, that tau y x y is equal to mu del u del y is actually a limiting expression of a Newtonian fluid for a 1D flow. We just argued in a more generic way, and that is exactly what I told when I started giving this lecture, that for a 2D flow field the angular deformation is not only limited to del u del y, but the angular deformation is del u del y plus del v del x. Therefore, for a 2D flow field one can argue that the shear stress tau x y is proportional to the summation of the total angular deformation, which is del u del y plus del v del x. And if you have a Newtonian fluid, of course, what is going to happen is tau x y is going to be mu into del u del y plus del v del x. So, that is actually an interesting concept. So, I mean, I will be happy if you pass on to the students this concept that this expression is valid for only an one dimensional flow field, right. For a more generic one, so if one really talks about a 3D flow field and 9-dimensional tensor and all stress tensor and all these things people talk about, in actually a 3D flow field, reality is, and you can understand it very nicely now, that tau x y and tau y x there is virtually no difference, because all you are trying to do is if you have a flow field like this, you now understand. So, if this is the coordinate system, we now understand that your shear stress is trying to deform an xy plane, right. So, this is an xy plane if you follow the coordinates. So, this is an xy plane, and this deformation can be caused by two ways. First, if there is a relative velocity between these two faces, and also if there is a relative velocity between these two faces. So, one of them depending on the direction, for example, this one will lead to del v del x, the other one will lead to del u del y, and therefore, as I mentioned that rather than a shell balance and talking about Newton's viscosity from there, I will prefer that if you have a good group of students, it is always a reasonable idea to talk about the generic form of deformation in a flow field, 2D flow field at least, and then extrapolate the concept to a 3D flow also, and then from there you actually correlate that your shear stress is proportional to the angular deformation, and of course, where the angular deformation shear stress is proportional to the angular deformation, which for a small deformation where the angular deformation is the summation of the two velocity gradients, and of course, where the shear stress is linearly proportional with the summation of the two velocity gradients, then you have a Newtonian fluid. The advantage is if one is looking at this definition of a Newtonian fluid, the moment one talks about an 1D flow, so depending on the flow field, one of the terms gets cancelled and one can very easily get to this expression. So, with that I think I will thank you for listening to this, and I will stop here, and in the next module I will pick up the conservation equations. Thank you.